You ever stare at a problem that's so complicated it just feels impossible? Like a tangled web where you can't even figure out where to start. Well, engineers deal with puzzles like that every single day. And today, we're going to dive into one of them, a real electrical labyrinth. We're going to learn the strategy they use to turn absolute chaos into perfect clarity. All right, here it is. This is our labyrinth. It's a direct current circuit, and it's got 19 different resistors and a 460-volt power source. Our one and only mission is to figure out a single number, the total electrical current that's flowing from that supply. I mean, look at this thing. It's a chaotic maze of wires and components, and that's exactly the point. So, yeah, where do you even start with something like this? It's totally overwhelming, right? Because it feels like every single part is connected to every other part. This is the kind of puzzle that makes you want to just throw your hands up and walk away before you even start. But here's the secret sauce. Solving this isn't about some flash of genius. Nope. It's all about strategy. The absolute core principle of engineering is taking a massive, complicated system and just breaking it down, piece by piece, into smaller, manageable chunks until the solution kind of just reveals itself. So let's get into it. Our goal right now is to tame this complexity. We're going to use a systematic method, a repeatable procedure that's designed to turn this visual mess into something perfectly logical. Okay, so to wrangle this beast, we've really only got two basic moves in our playbook. First up is what's called a series connection. That's when resistors are just lined up, one after another. You can think of it like making a single-lane road a little bit longer. The total resistance, well, it just adds up. Simple. The second move is a parallel connection. This is where the current splits up into multiple paths, kind of like a highway adding more lanes. And this move actually reduces the overall resistance, making it easier for the current to get through. And boom, here's our first move in action. Check out the left side. See those resistors, R13 and R14? They're in series, just a single path. So we just add their values, 200 plus 40 ohms. Now look at the right. They've been replaced by one single equivalent 240 ohm resistor. With just one simple calculation, the labyrinth is already a little bit less scary. Next up, we're going to tackle those parallel resistors. On the left, you can see all those different branching paths. After we apply the formula to collapse them, just look at the result on the right. That whole tangled section has been boiled down to just one 48 ohm resistor. This is the power of this method. Entire chunks of complexity just melt away. This timeline really shows the entire game plan. We start with absolute chaos. Then we combine the series elements. We collapse the parallel branches. And by just repeating these two simple moves over and over, we systematically tear down the complexity until the whole network is reduced to its simplest possible form. Now, this step-by-step simplification works beautifully for our puzzle today. But what about circuits that are, designed to be tricky? Puzzles that you can't untangle with just those two moves? Well, for that, engineers have a whole toolkit of advanced techniques. For example, what if the circuit had two power sources instead of just one? All of a sudden, our simple combine and conquer strategy, it just fails. The circuit becomes what we call irreducible, which means you just can't simplify it down to a single resistor anymore. To solve this, you need more powerful tools. One of the first tools they'll reach for is called mesh analysis. It's a pretty fascinating technique, actually. You basically draw these imaginary loop currents right onto the circuit diagram. Now, these loops aren't physically real, but what they do is let you create a system of equations that can solve for every real current, no matter how tangled the network gets. Pretty cool, right? And then there's Thevenin's theorem, which is just this incredibly elegant shortcut. It basically says that you can take any part of a linear circuit, I don't care how huge and complicated it is, and you can replace it with just one voltage source and one resistor that behave in the exact same way. It's like replacing a giant, snarled knot of rope with a single, simple loop. And believe me, the toolkit does not stop there. Engineers have this whole arsenal of specialized methods. You've got nodal analysis, the superposition theorem, Norton's theorem. Each one is like a different lens to view the problem through, a different key to unlock a specific kind of electrical puzzle. But hey, for our labyrinth, that simple step-by-step reduction was all we needed. So let's get back to it and see the final payoff. We've journeyed all the way from chaos, and now it's time for the clarity of a final answer. And here it is. After all that work, combining series, collapsing parallels, that entire 19 resistor network, from the perspective of the power source, behaves exactly like this one single resistor. We found the heart of the labyrinth. The total equivalent resistance of that whole maze is precisely 153 and 1/3 ohms. That single number captures the collective behavior of all 19 of those components. And now, we can finally answer our original question. Using the good old Ohm's law, voltage divided by resistance, we take our 460 volts, we divide by our total resistance, and we get the answer. The total current flowing out of that power supply is 3 amps. That's it. And this isn't some one-off party trick for just this problem. As the Handbook of Electric Power Calculations puts it, any reducible circuit, no matter how complicated it looks on paper, can be solved using this exact same method. It's a universal strategy for taming complexity. So why does this all matter? Well, because this process, the systematic simplifying of complexity, is the foundation of pretty much all electrical engineering. It's how we design the intricate circuits inside your phone, and it's how we analyze and manage the entire electrical grid that powers our world. It's an elegant and really powerful process for solving a static puzzle. But it does leave us with a final thought. What happens to the entire system if just one of those 19 components suddenly changes? It really makes you wonder just how fragile, or maybe how resilient, our complex, interconnected world actually is.